All right, we're going to start the year off with a review of integration. This section, I have to admit, it kind of has some weird things in it, but hopefully as I explain them, they won't be too weird for you. So just to start off, some of you need to review all of your derivatives and integrals, your justifications. So you need to start going over those and making sure you've got them. You might, as I suggest in the summer, go over some of the FRQs I did on YouTube, but you need to get your brain back thinking calculus. So basic substitution, this first one, you should all know this is just that. And so if you look at this, we have a problem because it only works when we have a single variable there. But in this case, we don't have a single variable. So we say to ourselves, golly gee, I wish there was just a single variable there because that'd be easy. So you make that happen by redefining a new variable. You define the single variable u to be 3 minus 4x. So now that gets us e to the u, which is fine and dandy, except I need a du because our variable, as you can see here, is u. So I need a du. But how do I get a du based upon what I know? Well, I take the derivative of both sides here. So du, derivative of 3 is 0, and the derivative of negative 4x is negative 4 dx. So I get this, and I say to myself, man, I wish there was a negative 4 dx here. That would be so awesome. So magically, I could put a negative, wow, can't see that, huh? Magically, I could put a negative 4 there, but I can't, that's just, I need a thinner line. I wish there was a negative 4 there. I can't just put a negative 4 because it changes it, but if I put a negative 1 over 4 in front, I just multiplied by, I multiplied by 1, so nothing changed. I just ate a hot pepper and my nose is running. Now, I can replace this with du, and I can't forget the negative 1/4 in front. So, this becomes a very simple problem. We copy the constant as just e to the u plus c. But what is e to the u? What is u? What is u? It's 3 minus 4x, and we are el duno, plus c. So that's a simple substitution when we have a basic integral, but instead of a variable, we have a function there. We say we want a single function, so we define a single function as that previous function and see if that works. So some of the techniques we're going to be doing over the next week are kind of crazy, kind of weird. And you don't want to jump to them first. You want to see if you have a simple basic substitution first. So you want to start with the simple before you go to the complex. So that is basic substitution. Now, subtle substitution is weird. It's just basically you're trying different things to get it to work. So I'm going to do something that's going to fail, and you'll see. I'm like, hey, what can I do? Let's make u e to the x. And you might think you're onto something, but du becomes e to the x dx. And now we're in a pickle, and I'll show you why. This becomes u plus, oh no, this is e to the negative x. E to the x is u, so we're kind of stuck here. So we have a couple of problems happening. So you might say to yourself, ooh, I don't know what to do. So then you might say, okay, let me make e or u the whole denominator, and then we start running into other problems. Oops-a-daisies. So using chain rule, we get minus e to the minus x dx. And now we have this big problem. This dx, what do I do with it? I have this ugly thing in front that I can't get there. So now we're stuck. So now it's time to give up on this problem and just quit, right? So there are weird secrets, and we're going to combine some weird things. And subtle substitution is just trying different types of substitution, but we're going to multiply by 1. But our 1 is going to look special. E to the x divided by e to the x is 1. So I'm going to multiply by this. And why would I do this? I don't know. It's just something, you just try crazy things. And there will be a method to the madness here. The top is very simple. But the bottom, what's e to the x times e to the x? Well, you add the exponents, so it's e to the 2x. And what's e to the x times e to the minus x? You add the exponents, you get 0. Huh. And that simplifies to this. Now, you might say to yourself, that's crazy. Who would ever think of doing this? Now, why would you think of doing this? It's because you realize when you take the derivative of e to the x, you're going to get an e to the x. And so du, if this is your u, so if your u happened to be e to the x, your du would be e to the x dx. And you want an e to the x, right? So it makes sense to multiply top and bottom by e to the x. Now you have the e to the x dx that you want for your du. So it works out nicely. So if you had some foresight, you may have realized, hey, multiplying by e to the x on top would be a good thing because the derivative of e to the x is e to the x dx. Now, let's substitute everything in. So if you look on top, these two, that's just u, which is kind of sweet. And then this is going to be u squared plus 1. I'm sorry, it's du. I messed up there, didn't I? Yeah, I meant to say du is that, and we have that here. So that's what's happening. So if you don't realize what happened here, using basic rules of algebra, this is e to the x squared plus 1 because you multiply. When you have an exponent raised to exponent, you multiply. So 2 times x is just your 2x. So this is just u squared. So we have that. And hopefully you remember your derivatives, antiderivatives. What form is this? You should recognize this as arctan u. If you don't, you need to study those. We're going to have a quiz on that, a really quick quiz. All right, but what is u? What is u? And bam, there is our complicated answer. And I know some of you are thinking, wow, that's crazy. Who would ever think of that? But hopefully you kind of saw where the reasoning comes from and why someone would be crazy to multiply by that form of 1. All right, split up fractions. This one's going to be even crazier. So you should realize that we can split this up into 2 separate fractions. So we are going to do this cos x over secant x dx plus the integral of sine cube x secant x dx. But what is secant? It's 1 over cosine. So this becomes cosine squared x dx. And this becomes sine cubed x cos x dx. And believe it or not, this one's easier. At this point, this one I'll have to explain. We really didn't, probably won't see this on the AP test, but I want to go over that, what you do with this. You do some things called angle reduction formulas. But before we do that, you can pause and try the right side. You should be able to do this as a review. And then after you unpause, I'll explain how to do the first one. So this is a basic identity. And then what we can do is we can rewrite this with replacing sine squared. So we know that cos squared plus sine squared equals 1. Therefore, sine squared x equals 1 minus cos squared x. We will take this and we will place it in for sine squared. And what that will do for us, that will get rid of the sine and we'll only have cosines. So we're going to have cosine of 2x equals cosine squared x minus 1 minus cosine squared x. And if we combine like terms and distribute the negative, we get this. It's 2 cosine squared x minus 1. Now, if you look here, we're trying to get rid of the cosine squared because we don't know the antiderivative of that. So if I solve for cosine squared, I add 1 to both sides. And then I divide both sides by 2. And I get what's called an angle reduction formula. So we get cos squared x is cos of 2x plus 1 over 2, which I can write as cos 2x over 2 plus 1/2. Either way, I reduce that squared. So it's called an angle reduction. So I'm going to replace this with that. It's going to get crazier. Sorry, guys and gals. Let me split this up into 2 separate integrals. Make my life a little easier. So now we have 3 integrals to do. Now, if you look at this, if this was just cosine of x, that's easy. The antiderivative is sine of x. But it's 2x. So we have to do a u sub and let u equal 2x. Du will be 2 dx. Do we have a 2 dx? Now we do. So let me lower this. So we have a 1/2 and the cos 2x, and that's actually, that 2 comes out in front, and so we'll make that a 1/4. And this will be cos u, and all this becomes du. And I will leave this nice and pretty. Here we have another substitution, and this might trip you out, but since I used u over here, I'm going to come up with a new variable. W will be sine x, because we have a function in a function, a sine in a cubed. So the inside function, which is the sine, we redefine as w, and this would be cos x dx. Oh, 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 I forgot the cos x from above. And here's what is nice and pretty. This appears there, so that replaced by dw. And beautiful things are happening. Isn't this fun? So much fun. I'm sure you all missed it. So the sine becomes w, and the cos x dx becomes dw. And now we're on our way. What's the antiderivative of cosine? That's just going to be sine u. What's the antiderivative of 1/2? That's just 1/2 x. And the antiderivative of w cubed is going to be w to the 4th over 4 plus c. Replace everything with what it's supposed to be. U is 2x. And w is sine x. Bam. I know that seems ugly, but if you just break it down to little pieces, it's nothing that's complicated. It's just like, who would ever think of doing that? That's just crazy answer. That's just only crazy people would do something like that. All right, so that technique is splitting up fractions, but we used an angle reduction identity. We used substitution, so a lot of things going on there. So we're just doing a massive review of integration. All right, long division. You could try to factor and cancel something out, but it's just not going to happen in this problem. So whenever the degree of the numerator is bigger or the same as the denominator, long division is a common technique. So we're going to divide x plus 4 into x squared plus 2x minus 1. We'll ask ourselves, x times what will get us x squared? And clearly it's going to be x. So in the x column, I put an x there. And then I just multiply this. So I get x squared plus 4x. And just like you learned in 6th grade, you subtract this. 2x minus 4x is minus 2x. X squared minus x squared is 0. You bring down the next one. And we go through the process again. I'll try to use another color here. So what times x equals negative 2x? Well, it's negative 2, so I put a negative 2 in the constant column. And then I multiply that. I get negative 2x minus 8. And I subtract that. Negative 2x minus 2x is 0. Negative 1 plus 8 will be 7. And so this is our quotient. This is a remainder. So now I can rewrite this beautifully as a quotient and a remainder over the divisor. And now it becomes a relatively simple problem. Except let me break it down into two parts. All right, first part is simple. X squared over 2 minus 2x. But what do we do with this funky looking thing here? And we realize, you know what? That x, if there's only an x, it would be easy. It would just be 7 ln of x. But it's a function. So we want the denominator to be a single variable. So we will let u equal x plus 4, making the denominator just a single variable. And then we find the derivative of u, which should just be dx. And now we just replace things. So the 7 I will leave there for now. The x plus 4 becomes u, and the dx becomes du. I have a rule. I can pull a constant out of an integral. And 1 over u, the antiderivative of that, is just ln, absolute u. But what is u? u is x plus 4. So that is my beautiful answer using long division. That actually appears on AP tests occasionally, not very often. So that is that. We are going to move on to another technique here. Completing the square. Woo! So you could try u-subbing, and you could try crazy things like, hey, let's try making u -7 minus 8x minus x squared. Du would become -8 minus 2x dx. And you have nothing like that here. And there's no way you can get it there. So craziness says that's not going to work. And so you're like, what can I do? This is like ugly. I have no clue. So here's what we're going to do. Complete the square. We're going to try to make the denominator. This is side work, by the way. We're going to factor out the negative sign. We get x squared plus 8x plus 7. And we're going to complete the square on the bottom. So what's the magic number we want there? So I don't know if you remember how to complete the square, but you take half of this and square it. So half of 8 is 4, and 4 squared is 16. So I want a 16 there. So what I do is I add 16, but if I add 16, I change the problem. I'm not allowed just to add 16 randomly. But if I subtract 16, those cancel each other out. So therefore, I did not change the problem. And doing a little more algebra, this factors to x plus 4 squared, and we get -9. Now I'm going to distribute the negative sign in there, and I'm going to get 9 minus x plus 4 squared. Craziness, right? Again, you would think, who would ever think of this? Crazy people. Crazy. So we're going to replace the denominator with this. Man, we're doing like hard integration problems. So this is great review. For the homework, I'm not going to give you a lot of problems to do, but it's kind of crazy. Now, once upon a time, you knew this. And this is arc sine x. And this almost looks like that, right? Almost. Except we want a 1 right there. So I'm actually going to back up and get a 1 there before we do all this silliness. So I'm actually able to factor out a 9. I'm going to get 1 minus, and we have x plus 4 squared over 9. And I'm going to go one more step. 1 minus, and I'm going to go x plus 4 over 3 squared. I don't know if you can see what just happened. Hopefully, if you don't, just pause, look over what happened. That's the equivalent. So now, beautifully, this becomes this. Now, remember this. This is your target that you're working on. Whoopsie. So here's the thing. You want a 1 there, and we have a 1. You want a variable squared, but we don't have a variable squared. And this 9 shouldn't be there. So very simply, what is the square root of 9? It's 3. So we're going to pull that 3 out front. And we're getting really close to what we want. This blob here, we want a single variable. So we're going to let u equal that blob. And then du is going to be 1/3 dx. Ah, whoa, so cool, so cool. Cool like drool. Watch this. All this gets replaced with u. And then this 1/3 dx gets replaced with du. So we'll do that next. Cool like drool. And then this is simply arc sine of u plus c. But what is u? This is so cool. U is x plus 4 over 3. Man, I think we have an answer. Let me double check to make sure I didn't lead you astray. I left out the fraction bar. Let's see. That is absolutely phantasmic. That's absolutely gorgeous. Like all of you. All right, we have one more to go. Hopefully this wasn't too long. This is craziness. Again, you might try this and say, oh, I got this. U is 1 plus cos x. Du is minus sine x dx. I need a minus sine dx. I wish I had a minus sign on top. We don't have that. I have no clue what to do. I have no clue. I'm lost. I have no idea whatsoever. This again is just craziness. So I don't know. It's just something that you learn from trig. If I can multiply the bottom by 1 minus cos x, it will combine to get 1 minus cosine squared, which is sine squared, which is kind of cool. But I can't just multiply the bottom, so I multiply the top and bottom. So this equals 1. I learned in, third grade? Anything times 1 is itself, so I haven't changed anything. So now, this becomes this over, and if you multiply and distribute all these things all over the place, yeah, you get 1 minus cos squared x. Now again, a reminder, cos squared x plus sine squared x equals 1. So therefore, sine squared x equals 1 minus cos squared x. So the bottom just becomes sine squared x. Ooh-ah, ooh-ah. And the top is 1 minus cos x. And it looks like we're making progress, but then we're stuck again. And some of you might think u sub, but this should be a technique we used earlier. We split this into 2 separate fractions. We make it 1 over sine squared x dx minus cos x over sine squared x dx. And we just do a little more manipulation. 1 over sine is cosecant squared. And the bottom, so I'm going to make it cos over sine, 1 over sine. And I just, through experience and knowing some common antiderivatives, I am led to this. But cosine over sine is cotan. And 1 over sine is cosecant. And beautiful things start to happen. The derivative of what is cosecant squared? This is again where you need to know your basic derivatives. So think about that. See if you can, you can pause if you want and try to see if you remember. But the antiderivative of cosecant squared is what? And if you remember, it's going to be cotan. The derivative of cotan is cosecant squared, but it's negative because it's a co. So it's going to be minus cotan x. And the derivative of what is cotan cosecant? Hopefully you remember this. The derivative of cosecant is minus cosecant cotan. We already have the minus there, so it's going to be plus cosecant x. And we have our wonderful, beautiful answer there. So that's some crazy, mind-blowing integration. If you're able to do that, you are a integration god. If not, hopefully you kind of understood some of the substitution things, and honestly, on an actual AP test, you really rarely see crazy integrations. But if you can do these, it's just reassuring that you are able to, and you have the basic ones down. So that's it for this lesson. Hopefully it made sense to you. Not that you'd be able to do it on the fly, but the steps made sense to you. All right. Great job. Way to hang in there for this first video. I'll talk to you guys later.